Right, welcome to video 2, the second revision video. Now in the previous video we looked at how light is eventually turned into kinetic energy, our movement energy, and how the light is transformed into chemical energy, and that chemical energy saved and stored in the muscles as ATP, potential energy, and then onto our muscle contractions. Now in this video we're going to look in more detail at energy itself, simple definitions for it, and the same for work and the same for power, and their simple application to practical examples. Now it's not a maths exam, but the examiners may require you to do some simple calculations. Now before we move on to work and power, we need to remind ourselves of the simple concepts of force and energy. So what is a force? Now we may not do A-level physics anymore, but a force is a pull or a push that alters or tends to alter the state of motion of a body. It makes it move, it makes it stop, it makes it accelerate, it makes it decelerate, it can change its shape. Those are the things that we need to understand about a force. More importantly, it is measured in newtons. Now energy, and this is the section from the textbook, energy is the ability to perform work or put mass into motion, and that's the simple concept that we need to understand. So from a practical point of view, when applied, energy refers to the ability of the muscles to contract, and that reminds us of our kinetic energy from the previous video. Now energy is usually measured in joules, and that's a joule is quite simply the force required to move 1 newton through a distance of 1 metre. Now later on in the syllabus we'll look at the concept of calories, because energy can also be measured in calories, and 1 calorie is equal to 4.18 joules. Now that may not seem important at the moment, but when we're going to do our work on pre-match meals and eating during performance and carbohydrate loading and so on, we look at the idea of how many calories we need to take on to power a certain event, be it a 1500 metre race, but also something longer, such as a half marathon, and maybe some sort of triathlon or Ironman. So let's look at our work. This is all to do with when a force is applied to a body to move it a certain distance. Now the equation that we'll look at and that we need to know and need to learn is that work equals force, measured in newtons, times by a distance moved, measured in meters, and the units of measurement for work are joules. Now 1 joule equals 1 newton, and that's acting over a distance of 1 metre. Now if we take an example of a rugby player, so if we have a 90 kilogram rugby player who is moving a distance of 1 metre, the force required to move that rugby player will be 900 newtons. You simply times 90 kilograms by 10. To move that rugby player 2 metres would be 1800 newtons. That would be the force that is required, and from that we can work out the work, which will be measured in joules. So when we move on to power, this is the equation that we need to be aware of. So power is the rate at which work is done and involves applying the concept of time. So work divided by time. More accurately, again, force measured in newtons times by a distance, which is always in meters, divided by the time, which is in seconds. And the units for power are watts. Now applying this idea of work and this idea of power, quite simply, force times by distance would be our strength, and as soon as we divide it by the time, we've got a concept of speed. Now if we can look at the following table at the bottom, we've got athletes of varying weights from 70, 75, 80 and 85, and we've got the time that they did the 100 metres sprinting, and the time is measured in seconds. What we want to look to do is rank these 100 metre sprinters listed in the table from the most powerful to the least powerful. Now I said it's not a maths exam, but this is one of those occasions when they could require you to do some simple mathematics. So let's try and use the numbers that we've got in the table here to come up with the power for each of the athletes over that distance in that time and then rank it. So let's take our 75 kilogram 100 meter sprinter. So if we look at the equation, force, distance, time. We need to work out the top of the equation first. So 75 times that by 10, and we're going to get our force in newtons. Times that by the distance, well, the distance quite simply is 100 meters. And then divide that by the time, which is measured in seconds. And that gives us 6,250 watts. Now if we did the same thing for each of the other athletes, we'd find that the 70 kilogram runner who ran it in 11 seconds had a power of 6,364 watts. And if we did the remaining two, we get the following figures. So if we were going to rank them, the most powerful athlete over that distance and the times that they've done it based on their weight would be as follows. What's worth noting is that actually the lightest athlete actually was ranked in third place and not last place. He or she did it in 11 seconds. So as soon as we apply the concept of time, a smaller athlete who can run quicker can generate more power. They can often be far more powerful than a bigger athlete who runs at a far slower time. But in this particular example, the 85 kilogram athlete who runs it in approximately 12 seconds has a power output of 7,083 watts. When it comes to our revision then, main focus is really going to be on the definitions for each of the three concepts, so energy, work and power, and the units that they're measured in. They should really be your main focus, and you also want to practice putting these equations, these simple equations, into practice. So the kind of things you're going to get asked in the exam, as in the table at the bottom, they'll give you some sort of an athlete with a weight, it'll be in kilograms, they'll give you some concept of the time that they are running or moving over, and you'll simply have to work out the power measured in watts for that particular athlete.